The Earth's subsurface is a vast, complex, and largely unexplored frontier, holding clues to our planet's past, present, and future. Understanding its hidden structures is crucial for a wide range of scientific and practical applications, from predicting natural hazards to locating vital resources. What are Earth's subsurface structures? The Earth's subsurface refers to the geological formations and layers found beneath the ground surface. These structures can range from shallow soil and rock layers to deep formations like faults, folds, and even the planet's core. They are primarily defined by changes in the physical properties of the materials, such as density, electrical conductivity, magnetic properties, and the way they transmit seismic waves. Key subsurface structures include sedimentary basins, large depressions filled with layers of sediment, often containing valuable resources like oil, natural gas, and groundwater. Faults, fractures in the Earth's crust where rocks have moved past each other. These are critical in understanding earthquake hazards. Folds, bends or curves in rock layers, often formed by compressive forces. Intrusions and extrusions, igneous rock bodies that have formed from solidified magma, either within the Earth, intrusions, or on the surface, extrusions. Aquifers, underground layers of permeable rock or sediment that can hold and transmit groundwater. Mineral deposits, concentrations of valuable minerals, often associated with specific geological structures. Magma chambers, reservoirs of molten rock beneath volcanoes. Methods for exploring Earth's subsurface. Since direct observation of the deep Earth is impossible, scientists rely on a combination of indirect methods and direct sampling techniques. 1. Geophysical methods. These techniques measure physical properties of the Earth to infer subsurface structures without disturbing them. Seismic surveys. The most detailed method, involving generating sound waves, using explosives or vibrators, and recording their reflections or refractions as they travel through different subsurface layers. Seismic reflection creates detailed images of subsurface layers and structures, widely used in oil and gas exploration. Seismic refraction measures wave velocities to determine the depth and thickness of layers. Gravity surveys measure variations in the Earth's gravitational field, which can indicate differences in rock density. Useful for identifying large-scale structures like salt domes or buried basement rock. Magnetic surveys detect variations in the Earth's magnetic field caused by the magnetic properties of subsurface rocks. Used to map faults, folds, and igneous intrusions. Electrical resistivity tomography (ERT) measures the electrical resistivity of materials by injecting current into the ground. Useful for mapping groundwater, contaminants, and certain rock types. Electromagnetic (EM) surveys induce an electromagnetic current in the ground and measure the resulting field, providing information about conductivity. Applied in mineral exploration and environmental studies. Ground-penetrating radar (GPR) uses high-frequency electromagnetic waves to image shallow subsurface features, up to tens of meters deep. Common in archaeological surveys, utility detection, and concrete imaging. 2. Direct sampling methods. These provide direct physical evidence of subsurface materials. Boreholes/drilling. The primary method for obtaining direct information. Drilling allows scientists to extract rock and soil samples, cores, for laboratory analysis, providing detailed data on material properties, rock types, and fluid content. Well logging involves lowering specialized tools into boreholes to measure various physical properties of the surrounding rock formations, such as resistivity, radioactivity, and porosity. 3. Remote sensing and geological mapping. While primarily focused on the surface, these techniques provide crucial context for subsurface interpretations. Satellite imagery and LiDAR provide high-resolution topographic data that can reveal subtle surface expressions of underlying geological structures. Geological mapping involves systematic documentation of rock types and structures visible at the surface, which can be extrapolated to infer subsurface conditions. Importance of studying Earth's interior. Understanding Earth's subsurface structures is vital for numerous reasons. Natural hazard assessment and mitigation. Knowledge of faults and rock formations helps in predicting and preparing for earthquakes, volcanic eruptions, and landslides. Resource exploration. Crucial for locating and managing natural resources such as hydrocarbons. Oil and gas. Subsurface imaging helps identify traps and reservoirs. Groundwater. Mapping aquifers is essential for sustainable water management. Minerals. Identifying geological settings favorable for mineral deposits. Geothermal energy. Understanding geothermal reservoirs for renewable energy. Civil engineering and construction. Essential for assessing ground stability, identifying potential hazards, like sinkholes or unstable foundations, and designing safe infrastructure. Environmental studies. Used to map contaminant plumes, understand groundwater flow, and assess sites for waste disposal. Scientific research. Provides fundamental insights into plate tectonics. How plates move and interact, driving geological processes. Earth's magnetic field. The geodynamo generated in the core, which protects Earth from solar radiation. Planetary evolution. Understanding Earth's interior helps in comparing it to other planets and celestial bodies. Climate change. Long-term climate patterns are influenced by internal Earth processes. In essence, exploring Earth's hidden depths is not just about scientific curiosity. It's about safeguarding our communities, managing resources responsibly, and deepening our understanding of the dynamic planet we inhabit.